Let's start then. Hello, everybody. My name is Luis Pascual, and I have the pleasure of introducing Eduardo Hernández Chambers, Eddie, who is our speaker today. It's a pleasure for me for several reasons. First of all, is that he's somebody from the house. I mean, he studied here. He studied in Alicante, his degree in chemistry, but then he came here to study quantum chemistry. Then he moved to the UK, to London, to the Royal Institution for a PhD there. And then after a couple of postdocs, he came back to Spain. He went to Barcelona, the Instituto de Ciencia de Materiales there. And then in 2010, he moved here to the Instituto de Ciencia de Materiales de Madrid, is where he is now. So he's somebody from house. Second is because it's a pleasure because he's a great communicator from my point of view. And he will be speaking about quite interesting topics today, such as AI, machine learning, material science, etc. And last but not least, because Eddie is a friend of mine. He's a very good old friend of mine from the quantum chemistry times here in the faculty. So it's a pleasure for me to introduce you. Oh.
Thank you very much, Jose Luis. Jose Luis didn't say it, but we've known each other for more than, 40 years now?
Oh, yeah.
At that time, we were young. Now we only look young.
We have best.
Yes. Okay, so thank you very much for this very nice introduction of Jose Luis. Thank you very much, all of you, for coming. I would like to keep this at a very informal level. So please, if you have any questions along the way, you don't have to wait until the end. Just feel free to raise your hand and ask. I'll try to clarify if I can. Okay. So this is the title of my talk today. I hope you can see it. It's a brief introduction to machine learning and some applications that I take from my recent work. Not because I think my work is particularly important, but because I'm more familiar with it than with the work of other people. And these applications will be in the general context of material science. So there you have my contact details if you care to reach out to me in the future. Okay, so I always like to start with a brief outline of what the talk is going to contain. So as people who generally work in the field of material science, and I mean material science in a very broad perspective to include chemistry, condensed matter physics, anything that is in one way or another related to materials. So we work in that field. I assume most of you do as well. So why should we care about artificial intelligence? In other words, can it be useful for us? Obviously, this is not too much of a spoiler. If the answer to this question was no, I wouldn't be giving this talk. I would be giving some other talk. So the answer is yes, as you can anticipate. But since we're talking about AI, what is it? Maybe not all of you are familiar with it. So I'd like to give you my own perspective of this. Okay, so then I will illustrate this brief introduction, this concept of AI, with some of the things that we have been doing in my group and with my collaborators in recent times. And the most dangerous part of this talk is going to be giving you my perspective of what may come about in the future in the connection between AI and materials. And of course, it's always very dangerous to make predictions, especially about the future, as someone said. Disclaimer, I want to make it clear at this stage that everything I'm going to be presenting is biased by my own experience and my own view on these topics. Nothing that I say should be taken as cut in stone. It's just my bias by my own experience, okay? But I hope I will not say anything that's not true, okay? So let's move on to, let's get into business. So should we take note of AI? Should we care about it? Can it be useful for us? So I think it would take a person living in complete isolation in a desert island and without communication to the rest of the world, not to have realized by now that we are in the midst of a technological revolution. It's the technological revolution of AI. And this, in turn, is fueling a scientific revolution, because I think it's fair to say that there isn't a single branch of knowledge, of science, of culture that has not been affected in one way or another by artificial intelligence by now. From biology all the way to chemistry, even in the social sciences and the humanities. I mean, even in the field of mathematics, pure mathematics, my idea of a pure mathematician is someone who sits at a desk with a piece of paper in front of him or her, with a pencil and a rubber, and is trying to demonstrate theorems all the time, right? And it would be difficult to imagine at first sight how AI could be useful to such a person. But in fact, only a little over a year ago, this paper was published in Nature, which describes how AI can be used to suggest, for example, statements of new theorems, potential theorems, that then mathematicians go away, sit down, and try to demonstrate. Okay, so even in that field where, in principle, one would be hard-pressed to find out an application of AI, it's being used. And much more in all the others, from chemistry, physics, medicine, etc. Okay, and going back to our own general field of things related with materials, this is data taken recently from the Web of Science, where I plot the number of papers that have been published over the last 30 years on a year-by-year basis that contain the combination of condensed matter or materials and AI, artificial intelligence, or machine learning. Okay, and you can see that this is really, this is where you can see that a revolution is taking place, right? Because only 10, 20 years ago, there weren't that many papers being published. Those are the vertical bars, the number of papers, right? Nowadays, you can count them in the several thousands published every year, right? So that when only 20 years ago, there were probably a few tens in 2006. And 30 years ago, when we were still young, there were practically none. Okay, so this is a very rapid evolution. And this wouldn't be happening if AI wasn't useful in the field of materials. So those several thousand papers that are published every year take tens of thousands of citations every year. So that shows again how interesting this combination of AI with materials actually is. And it's not just me who's saying this, it's not just the Web of Science. The Nobel Committee also thought so, because the Nobel Prizes in both physics and chemistry of 2024 were awarded to people that in one way or another were connected with AI or its application. So the Nobel Prize in Physics was awarded to John Hopfield and to Geoffrey Hinton, two people coming from the field of computer science, really, for their developments and inventions that made possible the development of neural networks. And I'm going to be telling you more about neural networks later in the talk. The Nobel Prize in Chemistry was awarded to 3 people, two of whom, Demis Hassabis and John Jumper, where they got the prize for developing AlphaFold. I don't know if you have heard about this, but it was the first time that someone developed a model that was capable of predicting the 3-dimensional structure of a protein purely from the sequence of amino acids that made up that protein. And this was a long-standing, difficult problem in biochemistry that was solved by the work of these 2 people, and that's why they got to share 1/2 of the Nobel Prize between them in chemistry. As far as I know, maybe this is not the only case, but as far as I know, this is one of the very few cases where both the Nobel Prize in Physics and Chemistry were awarded for similar research or research in the same topic. Okay, so should we care about it? What should we do about it? I think there are several levels to this question. First, at the individual level of you or me as scientists, it doesn't mean that we all need to become experts in artificial intelligence, but it's good to know that this is happening, and it's good to have a working understanding of the basics, for the simple reason that this may open new opportunities for you in your research. At the level of a group, hello, am I going too far? Am I running out of battery? Yeah, there we are. So at the group, at the level of a research group, knowing that this is happening, it may open opportunities for new collaborations with people who know about these things, with people that are familiar with AI and its applications. So it's good to know that what the potential is. Okay, and finally, there's a third level, which I call the collective level. That's the level, for example, of my own institute or the Faculty of Science here. At that level, I don't think we can afford to ignore this revolution, because we seriously risk, if we do that, being left behind. And trying to catch up is always more difficult than being at the forefront right at the beginning. So I think institutionally, an effort should be made to really be there at the beginning and exploit the potential that this brings. So to put it in the words of someone called Mark Cuban, Mark Cuban is one of these American entrepreneurs, not of the Bezos and Musk tribe. He actually supports Democrats. At least he used to, I don't know now, because everything is changing very rapidly over there. But, you know, Americans, they like these flashy statements. AI, DL, ML, so those stands for artificial intelligence, deep learning, machine learning. If you don't know it, whatever you're doing, if you don't understand it, learn it, because otherwise you're going to be a dinosaur within 3 years. Now, that's the kind of typical overstatement, American overstatement, that journalists love. I think this is a bit of an exaggeration, but it contains a grain of truth. As I was saying before, it's good to know that this is happening and to have some working idea of how it functions, because you never know when you're going to find it useful. And certainly others are doing it, right? If you surf the internet and look at the web pages of other research institutions around the world, here in Europe or in the US, Asia, everywhere, research institutes are having strong activity already in combining AI with materials. And I'm only speaking of material science. This is happening across the board in all branches of science. So we might as well do it too. Okay, so that's the general context. Should we care about AI? And I think we do. But what is it anyway? Let me give you my own view on that. So let's start with some definitions first. Artificial intelligence, machine learning, deep learning, these are terms that you probably come across frequently. They're often used quite interchangeably, but they mean slightly different things. So let's start with artificial intelligence. This is the general scope, right? Artificial intelligence has to do, is anything that has to do with emulating intelligence or even natural functioning of a living being, right? For example, a robotic arm in a factory, in a car factory, for example, is also artificial intelligence, even if we don't tend to associate it with AI quite so much. But the general field of robotics, anything that has to do with robotics, with thinking machines, that's what we call artificial intelligence. And it's a very broad field, somewhere in between engineering and science, with aspects of both. Then there is machine learning, and this is what I'm going to be concerned about with, today in more detail. So machine learning is actually a subfield of artificial intelligence, and it's that part of artificial intelligence that concerns itself with the development of algorithms and models that can learn from data. And I will elaborate on this a little bit more later on. And finally, there is deep learning. And deep learning, again, is a subfield of machine learning. It's that part of machine learning that is related with a specific kind of model, which is what we call neural nets or neural networks, which I will be explaining later in the talk. So the whole thing looks telescopically or visually like this. AI is the whole field, right? Then you have machine learning with tens, probably, of different algorithms that you can use in different kinds of problems. And within that, there is neural nets and deep learning when your neural networks have many layers of neurons. And this will become clear later in the talk, I hope. Okay, so machine learning and material science. So if you think about machine learning, you can see that this rests on three main pillars. On the one hand, we have models. We know what models are. We use them to represent nature or the world around us. Algorithms we also need because those algorithms are going to be used to train the models. And finally, the third pillar is data. Okay, so where does material science come in here? It comes because we've gotten very good over the years at producing data, right? Nowadays, we have data repositories for all kinds of materials, from crystallography databases, where we store information from experiments that tell us what a given crystal looks like. Databases for different types of materials like metal organic frameworks, covalent organic frameworks, polymers, you name it, there's a database for it. Databases of drugs, medicines, etc., spectroscopy data. All this is in some repository that you can go and consult, or you can, when you synthesize a new compound and do some experiments on it, you can deposit that data in the relevant database. Okay, so this is where the connection really lies. If we produce all this data, can we not get something more out of it by using machine learning? Because machine learning works with data, feeds upon data. So we might as well exploit it for doing that. Okay, so let's now consider, what does it mean, machine learning? What is entailed in a machine that learns? Obviously, you could think of downloading the entire contents of the Wikipedia into the hard drive of your laptop. But that doesn't mean that your computer all of a sudden has grown more intelligent, right? So it's data, yes, but we need to be able to do something that we couldn't do before with that data, right? So that is what machine learning is. There are several definitions that you can find in the literature. This is the one I find most appealing and most explanatory. So it states that a computer program is said to learn from experience E, and where you read experience, you can also interpret data, okay, with respect to some task T and some performance measure P, if the performance on the task T improves with experience, that is with more data. And I will try to clarify a little bit more what this means in practical terms. So this definition was given by Thomas Mitchell already 30 years ago. So let's try to put this into context a little bit. This is, to my mind, the general scheme of any machine learning algorithm program that you may encounter. So we have always this same structure. In comes some data, there's your model, it feeds on that data, and with the data, it makes a prediction, okay? And the model always depends on some parameters, which I collectively call sigma. There are also hyperparameters. We'll see what those mean next, but don't need to worry about those right now. Just let's consider the parameters. Okay, so in comes the data, the model processes it and makes a prediction with that data. Now, the prediction that is made directly or indirectly, implicitly or explicitly, depends on those parameters, sigma, right? So how good your prediction is will depend not only on the data, but especially on the parameters of the model. Okay, and depending on how good the prediction is, you can estimate the performance, how good the performance of the model is. Now, where is the learning here? The learning is in this key step here, that because the prediction depends on the parameters, the quality of the prediction depends on the parameters, you can always tweak the parameters of the model to make your prediction, its prediction, better. Okay, for example, okay, this you can define the performance in many different ways. This is one of the simplest ways that you can think of. So it's simply the square of the difference between the prediction and what we call the ground truth for this particular set of data, right? If the difference is large, this square is going to be even larger, and that will give you a poor performance, okay? But the point here is that performance is just a function. And if it is a function that depends on the parameter sigma, we can always calculate its gradient with respect to those parameters. And with that information, we have everything we need to modify the parameters, to tweak the parameters of the model to make its future predictions. So all we need to do is to move down the gradient of the performance because we want to move down the gradient to make the error in the prediction better. Okay, so essentially that's all that there is to it. Of course, it gets more complicated in actual practice, but that's the essence. That's what I think is the key point of machine learning. So let's see a particular example. Let's illustrate this with a particular case. It's the case of the problem of recognizing handwritten numbers, okay, by a computer program. As humans, we can do this very well, but how do you teach a computer program to do that? For that, what we need is lots of data. So lots of examples of handwritten numbers, but we also need that data to be labeled, to be adequately labeled. So we need to know, we need to tell our program that this is actually a 5, that this is a 0, and this is a 4, etc. Okay, because otherwise there's no way that the computer program can learn. How are we going to do this? There are different ways one could do it, but I want to illustrate it with the concept of a neural network. So here is the original concept. This is a drawing by our most famous scientist, Santiago Ramón y Cajal, of what he saw under the microscope when looking at the cut of a slice of brain. And here's the poor man's neural network, the crude imitation of what you have in nature. This is the simplest kind of neural network. It's called a multi-layer perceptron. So it's a flashy name for a simple model, but not so simple as we will see. Now, if we look at the components of neural networks in biological neural networks, you have neurons, where there's the nucleus. The nucleus is connected through the dendrites to other neurons before it, and it's connected to others further down the line by axon terminals. And we have the same in artificial neurons. Looking at more in a little bit more detail at the artificial neuron, this is what it does essentially. It's very simple. So in comes input in the form of numbers, x1, x2, x3, and potentially many more, right? Depending on how many neurons this other neuron is connected to. And those numbers are subject to a simple linear transformation. So they are summed together with some weights. And if you remember in my previous transparency, I spoke about sigma, the parameters of the model. These weights are some of the parameters of the neural network model. Okay, and there's also sometimes biases. So another number that you can tweak. So you weight your inputs to create a new value, which is the inner state of the neuron, right? And that new value is often fed through, but always, I'll explain why, through what we call an activation function, this F here, of which there are many different kinds, but we don't need to worry about that at the moment. Just the result of this linear transformation is fed through the activation function. That's what you need to know. So looking at the whole thing working together, in comes your input, let's say a vector of length 6 in this case, right? And you take that vector, you construct a new vector for the next line of neurons, the next layer of neurons, this way with the weights and the biases. And if you did nothing else, this would be a linear transformation, right? So you could feed this y value, this new y value, to the next neuron layer and so on. But doing that would be limiting the capacity of the model. Those would be two, in this example, linear transformations. Concatenating two linear transformations gives you overall a linear transformation. And what we want is our model to be nonlinear, right? So that's the role of the activation function there. So before we transmit the information further, we do this activation function business. And the reason for doing that is because nonlinear models have a greater expressive capacity, a higher flexibility to reproduce all the data than linear models do. So yeah, there's the activation function. And just to recap, the model parameters, the sigmas that I was referring to earlier on, those are the weights and the biases. And I also spoke about hyperparameters, if you remember. The hyperparameters are, for example, the number of neurons that you have in a particular layer, or how many layers of neurons you concatenate in the model. Those are things that you can play with to make your model better, right? And they define the physical structure of the model rather than the numerical parameters that define it. Okay, so let's see this in action. Pictorially speaking, we could use such a model, such a neural network, to resolve our problem of identifying handwritten numbers. So what's our number? This is just a photograph. It's a matrix of data, right? In this case, 28 by 28 pixels. In total, 784 values, where each value, when it's close to 0, means that that pixel is black. When it's 1 or closer to 1, it's a very white pixel. And everything in between, all the grays between black and white, are some intermediate values between 1 and 0. Okay, so we can, oops, sorry. Why is this not working? Okay, I had a very nice video here. Because I work with a Mac,
Maybe you can click.
let's see if that works. No, it doesn't. So go back. Never mind. It was a flashy video, but I'll just say it with words. So once the model is appropriately trained, this array, you spread it out as a vector, you feed it into the input layer. Yes, you had a question? I thought you raised your hand. No, okay, sorry. So you feed it into the input layer, and the information flows. Every value of every pixel is weighted by the appropriate W and added the bias and so on. And what you should get at the end is a series of values here, the largest of which is going to mean which number the neural network identifies, which value is assigned to this particular picture by the neural network. And if your neural network has been well trained, it should give you a 7, right? With a high probability. You can interpret the numbers that come out here as probabilities of the number being a 7, an 8, or whatever. And it should give you a very low probabilities for all the other numbers, perhaps not so low for a 1, because a 1 and a 7 can be easily confused even by us, right? Depending on how good or bad your handwriting is, or even a 4, which also could look like a 7, but it's going to be very difficult to confuse it with an 8 or with a 9 that look very, very different. Okay, so why are neural networks interesting models useful? I think I said it already. They have great expressive capacity because of the nonlinearity implicit in the model. And I've only shown you the most basic structure of a neural network. This multi-layer perceptron can actually be adapted to many different forms to tackle different kinds of problems, like, for example, dimensionality reduction. They are frequently used in image recognition or image classification. You can even make them recurrent so that you can predict data that is dependent on time, so trajectories, for example, or video sequences. And also there is the mathematical theorem that I haven't studied, but I know it exists, saying that neural networks are universal approximators. That means that no matter how complicated the function you want to imitate, to reproduce, you can always define a neural network that approximates it sufficiently well. I'm sure if the previous video didn't work, this one isn't going to work either. But I wanted to illustrate this with a simple example. So we have this function, one-dimensional function, which has an oscillatory component and the amplitude of which decays with x. Can we find a neural network? Can we train a neural network to reproduce this data? Obviously, the answer is yes. I tried a very simple neural network with just 10 neurons per layer, an input layer that takes the value of x, its square, and the cube. I promise that this looked fine in my own Mac, but changing information from Mac to Windows always spoils things. So the outcome of this network should be the value of x, the value of the function at x. Okay, so wonderful, it works. I didn't expect that. So okay, so yeah. Let me go back. Yeah. What I'm not going to be able to do is to stop the video where I wanted, but you can see these are different stages of the training of the neural network to reproduce the data. And by the end of it, you see that it does a very good job. But this is kind of cheating because so the red function, which is my ground truth, what I want to reproduce, I pretended here that I knew it at almost every point, so something like 200 points. The model that I defined, this neural network, has a total of 161 trainable parameters. So my sigma is a vector of 161, which is quite a lot, right? But I'm using a lot of information to train it. But the magic of neural networks is that you can do the same job pretty nicely with much less information, which is typically the case in which you find yourself in practical applications. So I'm doing the same job here, but only with assuming that I know the function in only 20 points, which are a lot fewer than your 160 odd parameters, right? And you can see that even in this case, the neural network is able to learn pretty well the values of the function. And once you have trained it, you can make a prediction of what the function looks like everywhere, not just where you know what it is. And you can see that, okay, the model is not so good everywhere as it was before. Particularly, it can never guess precisely with 100% accuracy what the function is going to be like there where it has no information. But even so, it doesn't do a bad job even in those regions where it wasn't trained, right? So this gives you an idea of the flexibility of neural networks. Okay, so as I said before, I only showed you here so far the most basic type of neural network, this concatenation of layers of neurons, but you can make them in very different ways. For example, neural networks that are very commonly used nowadays in everything that has to do with image processing, they're called convolutional neural networks, and they are designed to mimic somewhat the structure of the visual cortex in the brain of animals or humans. And they are really very good at classifying images, identifying images, and different operations that you might want to do with image information. You can also have recurrent neural networks that I already mentioned to predict data that is dependent on time or sequential data, let's say, such as video data, etc. But actually, neural networks can do very much more than the kind of trivial examples that I've given you. Can anyone tell me what's in common with these between these pictures? Does anyone know?
They're smiling.
They're smiling. Good point. But it's not the answer that I'm looking for. Anyone? I mean, even if you know it, you can tell me. So the common point is that none of these people exist, right? They are figments of the imagination of an artificial intelligence model, some kind of generative neural network. Generative means exactly that once I know what a human face looks like as a neural network, I can invent new examples of it. So if you're able to have a model that can recognize what are the defining characteristics of a human face, We have two eyes, a nose, two ears, etc. This kind of model, this generative kind of model, can generate new examples of it. I think they're much better. So these pictures are already a few years old, and you can see that they are not perfect. For example, this lady here has one earring on one ear and not on the other. This could be fashion, right? But no, it's a mistake that the generative model makes. This one here has two earrings, but they're both different. Small mistakes. I'm sure they do it much better now. But the question this begs, remember, we are interested in materials or in science in general. We don't care so much about pretty pictures. If this can be done with something as complex and as ill-defined as a face, as a human face, could we not ask some generative AI model to give us new materials, for example, new materials that may have made to measure properties like a given band gap or a given hardness? We'll come back to that. Okay, so let's see how we're doing with time. I'd like to illustrate what I've been doing with AI in this last few years with some quick examples. As I said, they're not particularly important. They're just very familiar to me because I was heavily involved in them. So the first example is this one. It has to do with analyzing experimental samples by colleagues of mine in our institute. So my colleagues, they are very good at synthesizing 2D materials. One example is this molybdenum disulfate flakes. And when they look like this in idealized pictures, it's a layered material, right? And when you synthesize it in the lab, often they come in the shape, these funny triangular shapes, and they may consist of several layers, right, stuck together. Not always, sometimes it's just a single layer, but you may get two, you may get three. And because in experimental samples, they can have hundreds or thousands of these flakes, they need a rapid characterization tool that tells them for each flake how many layers it is. And not only that, they need to know whether the layers, what's the angle of orientation between them, because they are not necessarily growing in the perfect crystallographic orientation that you would expect if they were grown in equilibrium, because often they are synthesized in conditions that depart very strongly from thermodynamic equilibrium. And the point is that the properties of the resulting flake depend sensitively. For example, the optical properties depend on the angle of mismatch between two consecutive layers. So it was important for them to have a quick characterization tool. So we went away, we scratched our heads, and we developed a couple of models to do this for them very, very quickly. And we published this in Nano Letters a couple of years ago already. So that was just a quick example. We did this with different types of neural networks. But let me not stop there, because I have more interesting applications to show you, I hope. And one that I find more interesting is what is called in the field spectral reconstruction. So this has to do with spectroscopy. If you have ever been in a spectroscopy lab, typically the apparatus that people have to use to detect spectra, they are big and bulky, because if it's optical spectroscopy, you need long paths for your waves to have high accuracy and so on. But if your spectrographs were portable, there would be lots of applications that you could use them for. For example, in the food industry or in agriculture, to check whether the apples in your trees have reached the point of of maturity where you can collect them, right? So you could do this very easily with a simple spectroscopy measurement. So it would be nice to have small portable spectrographs, even if they are not as accurate as what you have in the lab. So how can we do this? How can we miniaturize spectrographs? The idea that we exploited, and again, this is the result of a collaboration with a group in an experimental group in my institute, the 2D Foundry group. An idea would be to use an array of LEDs, of light-emitting diodes. So a light-emitting diode is a device where if you circulate the current through it, it will emit light, right? If the current is intensive, it has enough intensity. And it will emit light in a given color, depending on the band gap of the device, and you could use actually an array of LEDs with different sensitivities to light as light sensors, okay? So if you shine light on an LED, the opposite of making a current circulate, you shine light on it, it will generate what's called a photocurrent, okay? So the idea is this. So you can see here, this is one of the devices that my colleagues, my experimental colleagues work with. Each of those LEDs there has a different sensitivity to the light. This sensitivity, in other words, is telling you, if I get light at this frequency, I'm going to generate a photocurrent of so much intensity, right? So the idea is this. The device, when illuminated by a given light with a certain spectrum, the gray peak there is going to generate as many photocurrents with their corresponding intensities as sensors, as LEDs I have in the array. And the question is now, can I use this information to go the other way around? So from the measurement of the photocurrents, without knowing what the incident spectrum is, can I reconstruct it? And this is the typical job for a neural network, and that's actually what we did. We trained the neural network to recognize with photocurrents like this, photocurrent intensities, what the incident spectrum that caused them actually was. And it works very well. So here's an illustration of three different spectra, the blue lines. These are synthetic spectra, right? And they're not real. They are spectra that we invented just to train the model. But we could calculate what photocurrents such spectra would generate. And the reason we had to do this was because we didn't have enough experimental data. We didn't have enough spectra, measured spectra, to be able to train the model. But we could generate it. We could invent, so to speak, those spectra, calculate the corresponding photocurrents, and train the neural network that way. So it's very good at reconstructing fictitious blue spectra. You see the red is the prediction, but it actually turns out to work also with real spectrum. So now the blue is actually real spectra measured in the lab. My colleagues measured the photocurrents. They told me what the photocurrents were. I fed them through my model, and the red lines are the predictions of the model. So you can see that it's not perfect, but it's working decently. Finally, I would like to touch on which I think is the most interesting application that we did so far. It's connected with the business of the pharmaceutical industry. You might have heard that in the path from synthesizing a new potential drug until it comes out in the market, that process can take years, and also it can cost lots of money to the pharmaceutical industry, even millions of dollars, and several years of experimental testing. And one of the reasons why that happens is because, of course, you need to make sure that a new drug is actually good for the patient. It's not, if you're trying to cure someone from a common cold, you don't want to give them cancer by giving them something that is poisonous, right? So you have to very thoroughly test your compounds. And one of the tests is what's called the Ames mutagenicity test, which is a test, the current gold standard of the pharmaceutical industry, to check whether a given compound is capable of producing mutations. Okay, the way this works is an experimental test, and the way this works is it takes 5 different strains of the bacteria Salmonella typhimurium, right? So 5 strains means 5 mutated families of this bacterium, which are mutated in such a way that they cannot grow, they cannot reproduce in the absence of histidine. Right? So the idea goes like this. You put each of those strains in contact with the compound that you're trying to test to see whether it's mutagenic or not. If the compound is mutagenic, if the potential new drug is mutagenic, it's going to eventually cause mutations in one or more of these mutations of the strains of the bacteria, eventually allowing it to grow even in the absence of histidine. Don't ask me about the biological details of this, but that's how it works, okay? So here it is summarized. There's your chemical to be tested. You put it in contact with populations of the 5 strains of the bacterium, and if any of those strains is able to grow, then yes, the compound is potentially mutagenic, so you don't want to use it. If none of them grow, then in principle, it is safe. Now, this is, as I said, an experimental test. It's very costly to carry out, and it's not always conclusive because there's the variable of time. How long should you keep your compound in contact with the bacteria before you convince yourself that it's not mutagenic, right? So because of all of this, it's not always the case that the pharmaceutical industry does this test very carefully. They don't always use the 5 strains. It's important to use the 5 because they are sensitive to different types of mutations. But anyway, you know what business is like. You cut corners if you can save money, etc. So it would be ideal, it would be good, probably the pharmaceutical industry would give us lots of money if we could develop a test that was, rather than in vitro, in silico, right? So in other words, a model that was able to predict the outcome of the Ames mutagenicity test. So this is what we have been working on, and it actually works very nicely. So I'm running short of time. I don't want to go into too much detail, but this is the general scheme of what the model looks like. So there's your compound that you want to check, this funny benzene ring with some functional group next to it. It might be mutagenic. You want to predict whether it's mutagenic or not. Now, I showed you earlier how you can feed data into a neural network model. But what do you do about information like this? You cannot take a picture of a molecule, right? But you can represent molecules and, in general, atomic structures by means of graphs. Right? A graph is nothing other than a generalization of the concept of a matrix or an array of pixels, right? Only that the relation between nodes in your graph is not necessarily the same everywhere in the graph. While in a matrix, every matrix element is connected, it has 4 nearest neighbors and another 4 second nearest neighbors. That's not always the case in a graph, but it's just a generalization of data representation, okay? So you can make models that work with graph information input, and that's what we did. And what we did was to develop what's called in the jargon a multitask neural network. Multitask meaning that we don't want to predict just the outcome of the Ames test, whether the molecule is mutagenic or not. We want to predict that each of the individual outcomes for each of the strains of the Trifimurium bacterium. Why? Because, as I said before, each of those strains is sensitive, reacts to a different kind of mutation and alerts you to a different kind of mutation. So we're not interested only in the global outcome, but we want the individual outcomes for each of the strains. So our model works out very nicely. It's able to give you a fairly accurate mutagenicity prediction, but beyond that, it's able also to recognize particular functional groups that are known in the literature by the experts to be causing mutagenic. So it recognizes those functional groups as alerts, structural alerts. Beyond that, it is informed because of the way in which we provide the data. It is informed about the molecular context, because it so happens that it's not just structural alerts, particular functional groups that cause mutagenicity. It depends on where they are in the molecule. In other words, what they are connected to. And our model is able to recognize that molecular context. And finally, the importance of that molecular context. Finally, it allows us to highlight, to predict the existence of new, formerly not known or not recognized, potentially mutagenic structural alerts that were not known. What I was referring to as the molecular context, you have this particular group which is known or is associated to mutagenicity in many cases. But what our model shows us is that it can be there in a molecule that turns out not to be mutagenic, and in others that are. And what makes the difference is the context, the molecular context. So in this case, it's mutagenic. It causes mutagenicity because of being close to a series of benzene rings, while if it's not in contact with aromaticity, it's potentially safe, right? So all this was revealed by our model. And as I said, also it allows us to find potentially new mutagenic structural alerts that were not previously recognized. So this work is now complete and in the process of being hopefully published. Soon it's the work of my postdoc, Abigail Teichen. And that's my last example, but there are many other fields in the kind of topics that we like, chemistry, physics, so on, in which you could find applications for machine learning. And here's just a quick list, but I'm not going to read it. I'm going to skip it because I want to touch very briefly on the last point, which, if you remember, earlier I asked, with generative machine learning, could we not generate new materials? That's something that I think is already happening. It's not so much in the future. So we saw this example, but it's already been done with, for example, organic molecules, you have generative algorithms that propose new molecules. But even you have this for materials. So what I'm showing here is an animation of a series of suggestions by generative algorithms of materials. So if you read this paper, you will learn everything about what this was. But essentially, it's a generative algorithm that proposes a new type of material with, I don't remember whether it was a specific band gap or some other property. The idea was, you ask the algorithm, give me a material that has this property, and it goes and does it for you. Then you have to test it in the lab, of course. And it might be difficult to synthesize. But in principle, this is being done already. So just to conclude now, I hope that I answered in the positive. I hope that I convinced you when I asked that question. Can machine learning be useful for us? I hope yes. I tried to provide, in the time that I had, my own perspective of what machine learning is. But there were inevitably many things that I could not cover, partly because I'm not an expert in everything. So many things were left in the input. But you can go and learn about them yourself. Very interesting. So yeah, that's all. Thank you very much.
Yeah, totally. So that's all for the speaking. Now it's time for discussion.
You mentioned mathematical theory, the neural network can approximate any function.
Yes,
I assume this is a mathematical function.
I presume so. Yes, I haven't.
And is it a constructive? I mean, is there a constructive method associated to the theorem? I mean, it provides a method to construct the neural network to approximate whatever function you have.
So I know the statement of the theorem. I don't know the proof, and I don't know under what conditions it applies. I don't think it gives you a constructive procedure. I think it's more a proof of a kind of existence or possibility that no matter how complicated your function is, in principle, you can approximate it by means of a model with the general structure of a neural network. But I don't think it's so general that it tells you how to do it in every particular case. That's. But I can try to fish it up and give you a more exact.
Yeah, actually, I mean, what it tells you is that you just need a hidden layer to reproduce any kind of function, but it doesn't tell you exactly how many neurons you need. And that's the reason, if I can reproduce a function with a single layer, why do I need to do deep learning? And that's the answer to your question. No, it doesn't give you essentially any practical recipe. And that's the reason why people, instead of a single layer, they construct models like yours, essentially with many layers. That's still much more efficient because the theory doesn't tell you, for instance, doesn't give you a number of neurons of this single layer is able to reproduce. But the theorem is trivial, almost stupid, okay? Because if you take a sigmoid, it can show easily and graphically that you can reproduce any function as long as it's analytical. So it doesn't guide you. I mean, it's nice to have it, but it doesn't help.
More questions? Comments?
Can I ask you something about the example of the photocurrents? And
Yes.
But this is an example of an inversion problem, right? And
Yes, exactly.
You might run into the problem that maybe there's not a single solution, right? When you invert this, do you take care of that somehow? I mean, you see what I mean, right?
Yes, yes. No, I don't take care of it. And in my short experience of this, I never encountered that difficulty. But you're absolutely right. There's no guarantee. I mean, it's a little bit like the theorem, right? If you have enough LEDs, the more you have, the more sure you're going to be that the spectrum that you predict will be closer to the real spectrum generating those photocurrents. But of course, here we were only working with, well, the LED array had 12 LEDs, but one of them was not functioning. So we had to work with 11, but it worked. In every case, well, rather than every case, I cannot say that with absolute certainty, but I was never aware of a case in which it didn't work. But yes, the answer is put more LEDs or sensitive devices to give you more information, and then
because in principle, I mean, two different distributions of current could lead to the same spectrum.
Yes.
You don't know in principle, right?
yes,
And that would be, well, there are tricks essentially to discriminate between those again. So, but yeah, very nice example. Thank you.
thank you.
More question?
Very nice talk.
Thank you.
I was wondering, how do you deal when you want to predict like properties or parameters, but they are coupled in between?
Okay, that's a very nice question because this is exactly what a multitask model does, right? So the reason we did it with this, like this, is because you can imagine that something that goes. Let me try to express myself better. So anything that causes a mutation in one of the strands may be affecting the other strands, perhaps not so much to cause a mutation, but what I'm trying to say is that you know, the outcome of these individual tasks it is not necessarily unrelated. Right. So it makes sense to have a model like this where you have a common branch where you process the input information and then feed that to submodels, which more or less they all have the same initial context that comes from the main trunk of the model. Right. So actually, we played around with using this exact same structure to predict properties of molecules, different properties that are somehow related between themselves. Like, for example, the total energy and I don't know, vibrational properties or the band gap of the envelope band gap in the molecule. All those properties, you don't have an equation that relates them, but somehow they are related between them. There is some mutual influence of one in the other, and this kind of model, this multitask model, is designed to recognize that kind of situation and exploit it. So.
Any more questions?
I have a question concerning something which is not of condensed matter, is about astronomy, which is part of my hobby. And when I observe solar disk through a telescope, depending on the focal length and the aperture, of course, you have the ID disk as a limit for the resolution.
Mm-hmm.
And then if the granulation is very small for that telescope, then there is a mixing between the granule and the boundary itself. So in the end, what you have is the same size for the ground and for the boundary.
Mhm.
However, you still by single eye can trace the granulation boundaries very easily because somehow your brain is used to.
Mhm.
But it's very difficult to deconvolute that. And although there are some algorithms, of course, in the large telescopes for professional people, but I wonder if my brain can trace this limit just by doing like this. It would be possible to use this AI to train somehow an algorithm that could reduce this boundary to something more close to the thickness that the boundary should have.
Um, I don't know, to be honest, but it sounds like the kind of problem that you could solve if the difference that you're speaking of can be captured in a picture. If you can take a photo and see it in the photo, then for sure you can design a neural network algorithm or even a simpler kind of machine learning algorithm, because neural networks are not the only thing, right? That was able to do the kind of operation that you described. So I feel sure that the answer is yes, although I'm not sure of the details, but I think it should be possible.
And the idea that I had in mind would be something like, okay, take a native picture of a large telescope, for example, in which you have very good resolution, and take a picture with lower resolution exactly at the same time,
Yes.
and compare both the high resolution and the lower resolution, and train somehow an algorithm to be able to convert this into this
Yes.
without going into the convolution process or anything like
Yes.
that.
There are algorithms for doing exactly that. Yes. I'm trying to remember the name of one now, but yes, two pictures of the same scene, say, taken with under different conditions and converting one into the other, or training the algorithm to learn that the two are the same. Yes, that's a very classical problem of this kind of algorithm. So, yeah, I think it should be possible.
Curious about the size, small size of your training data. Like if the example of the sulfide crystals, because there are some fields that you have huge data like
Yes.
genetics, but in some experimental fields, when you are fabricating a material, it depends a lot of the process, and maybe a PhD thesis had between 100 and 200 samples.
Yes.
So is it possible and realistic to work with a field?
That's a very nice and very important question. I said it at the beginning that AI and machine learning feeds on data, and this is very much the Achilles heel of these techniques. But I think with some ingenuity, you can always work around. You can find a strategy to bypass the problem when you don't have enough real data. And I gave you this example here, right? We all know what. So here we had exactly that problem. We didn't have enough experimental data to use to train the model for the spectral inversion problem. But we all know what spectra look like, right? You have peaks, which generally can be Gaussian or Lorentzian or some combination of the two, and you may have one at least, up to several. So we know what spectra look like. Let's generate them, even if they don't exist, if they don't correspond to any real sample. For the The other problem that you mentioned, this one, we had to do exactly the same. Here, all we knew was that these flakes tend to grow in the simple shape of triangles. It's very easy to generate thousands of images like this with triangles one on top of the other and rotated in random angles, and to train the model to recognize the angle from fictitious images rather than images obtained in the lab, of which we had, but only a few, because they were difficult to characterize and take directly from samples. Okay, so yeah, there's always well, not always, but often you can work around the limitations of data that you have in problems of this kind. So thank you for the question. That was a very nice question.
No more questions? Okay, let's thank.
So thank you very much.